Hey, Michaela and Makita. Anybody have any questions? While we wait for everybody else, we're way early, of course.
No questions from me.
That's cool. We're going to work on chapter 30 again today. I'm not sure we'll be able to finish it, but we'll get into at least LR circuits, maybe LRC circuits, hopefully. Hey, Jacqueline and Sean, y'all have any questions?
No, I'm good.
Okay. Just waiting for everybody else to show up. Got about 2 minutes before class starts. Almost time. All right, got another person in. We're up to 7 students. I think I've only had one drop, so we should definitely have more than this. All right, now it's officially past time for class to start, so I'm going to go ahead and start. Anybody have any questions? I know I've asked just about everyone. I think the only one I didn't ask was Alexi. Anybody have any questions before we start? That is a no. So last time we were talking about chapter 30, and I ended up like completely losing track of time and went about 10 minutes over before I even noticed I was past the time class is ending. I apologize for that. I'll try to keep an eye on it. Y'all feel free to let me know. I will not consider it rude or disrespectful or anything like that. If I do go over, we can still record, or if I have to finish a thought, I'll go ahead and keep on recording. Y'all don't have to stay there. And once the video gets posted, it'll be there at the end. Last time I did have some difficulties though. Excuse me, not last time, but Tuesday I had difficulties, excuse me, Monday I had difficulties with it uploading. And then Wednesday, I was trying to upload the Monday's version and that still had difficulties. And then finally I didn't get everything else. Monday and Wednesday didn't get loaded until Thursday. So hopefully everybody caught those. But the last thing I did was I got into not only mutual inductance, which we had worked out, and I showed you there's pretty much one problem that we'd solve in mutual inductance, and that's pretty much the example from the book. But we got into self-inductance, and I talked to you about how that is sort of a what we'd call a capstone problem for several chapters of the book. So one of the capstone problems for several chapters of the book was taking either Coulomb's law or more likely Gauss's law and finding an electric field for a certain symmetry. The symmetries for Gauss's law, of course, were infinite planes, cylindrical, or spherical. And then the second step would be, now that you have the electric field, use V equals a negative integral E dot dl to calculate the voltage difference between two parts, and then use the definition of capacitance C equals Q over V to calculate the capacitance of one of those three shapes. So that's a very typical problem. I think you saw it on the midterm. And while I'm there, let me remind everybody, my plan, I think I might not have announced this already with your class because I had one person that had to take it later, so I couldn't tell them that until after they'd taken it. But the deal is, if you fail this midterm or didn't do that well in the midterm, it's not the end of the world, because if you figure out better how to study so that you can pass a face-to-face slash test where you're being watched and not allowed to surf the internet and all that good stuff, if you figure out how to do that by the final, then if you make a better grade on your final exam than you did on your midterm, I'll replace that midterm grade with your final exam grade. I won't do it the other way around, but I'll do it that way. So y'all still have a chance to make your A. Nothing's written in stone. You can still pull this off. Now back to the capstone problem. So now that I've told you the capstone problem from the first, say, chapters 21 through maybe 25, the capstone problem for chapters 25 through maybe 29, 30 is really using either Ampere's law or the law of B of art to compute a magnetic field around a particular shape, specifically a solenoid, toroid, or a coaxial cable. And then from that, use the definition of flux, which is the magnetic flux is equal to the integral of B dot dA to calculate the magnetic flux. And then use L is equal to N times phi over B. I mean, excuse me, N times phi over I, the current, to calculate the inductance of one of those three shapes. Okay, so you should be able to do all three of those shapes. I did the solenoid first last time, and then I did the coaxial cable, which is what made me run over time. So make sure y'all catch the end of that video. Now I'm going to do a toroid, so you guys will have some sense of how to do this again. So remember, the rule is you're going to do amperes or Biot-Savart law to calculate a magnetic field for a very specific geometry. That'll be either a solenoid, a coaxial cable, or a toroid. And then you're going to use the magnetic flux phi sub B is equal to the integral of B dot dA to calculate the flux. And then you're going to use L, the inductance, or self-inductance, is equal to N, the number of turns, times the magnetic flux divided by the current. And all of that will allow you to calculate the inductance. So anybody have any questions on that before I jump into this first example? Okay, so what I'm going to do is example one. Example one is, let me turn on the document cam. I'm going to ask that we try to find the inductance. So we want to know what the inductance is for a toroid. So I'll say L equals question mark for toroid. And that's a terrible looking T, sorry about that. For a toroid of radiuses, and I'll make sense of that in a second, R and big R, and turns N, carrying a current I. So it's kind of a pain to draw a toroid, but what I'm going to get you to do is imagine this is a wire coming out, a current coming out of the page, and this is the current coming into the page. And then, of course, this wire will then go over to here and present another wire. In other words, it curves over to here like this. And you get another one coming out and another one going in. The net effect is, of course, you have a big radius for a circle, radius R, and then you have an itty bitty radius, little r. Okay. So the major point here being that little r is probably going to be way, way smaller than big R. And if it's not, we just have to use a little bit more robust techniques to deal with it. Okay. So we're first going to apply Ampere's law. So that's step one. And Ampere's law, of course, is the closed integral of B dot dL is equal to mu 0 times I enclosed. So I am going to make a hypothesis. and that is that B is equal to some B of R. I actually can write that as a little r for best results. So let's say B of little r times theta hat. And I'm going to show you why I believe it's theta hat, not negative theta hat or something like that in a second. Another student coming in. Okay, so what we think is happening here is, since this magnetic field caused by this wire is going in this direction, you see that this one's going to do the same thing, and they're all going to work together to make a magnetic field that travels along concentrically along the center of this solenoid like this. Okay, even though that didn't quite look like it. But this R can either refer to the inner radius, the outer radius, or the middle. It really doesn't matter. I'm going to pretend like right now it's to the middle. Okay. But the main thing is, if I now draw my coordinate system as this is my positive X and this is my positive Y, then Z will be going into the board. But the main thing is, you see that, yeah, the magnetic field points in the theta hat direction. Okay, remember theta goes basically this way from the positive x-axis towards the positive y-axis. We normally say counterclockwise, but that's when I draw it in a different orientation. In this case, this is the positive sense, so it's okay. Okay, so now that I have that, I'm going to solve the left-hand side of Ampere's law. The left-hand side of Ampere's law is B dot dl, the closed integral of that. So I'm going to have the integral of B of R theta hat dotted with R d theta hat, because that's a little line element that's going along the path of the magnetic field. And notice that is in the positive sense for the current. The current that you wish to get has to go, if you're saying the magnetic field goes this way, then the current must be going into the page in the middle, and that's what these little X's are doing. Okay, so it will in fact result in a positive current for these positives, for these X's down here. So it turns out, like I said, since I'm going to assume R is very small compared to big R, then R minus R and R plus R is essentially R. So I'm going to call this 2 pi R times B of R. And that should be a big R as well. So that's the left-hand side of Ampere's law. The right-hand side of Ampere's law is mu zero I enclosed. Now, the mu zero is straightforward, but we're going to have n terms in here, and all of them are going in the positive sense of direction. So I'm going to have mu zero n times I, where I is that current I said is going through it. Now I'll set the left-hand side equal to the right-hand side, like we always did with Gauss's law as well as Ampere's law. And I'm going to have 2 pi R times B of R is equal to mu zero n times I R. B is equal to mu zero n times I over 2 pi R theta hat for, or I should say for inside. Okay, in other words, inside the toroid. So we're basically ignoring the fact that there's probably going to be some residual magnetic field out here and in here, but it's very small compared to this. So now we've done step one, which is apply Ampere's law. Now I want to apply step two, which is apply the magnetic flux definition, which equals the integral of B dot dA to find out the magnetic flux. Well, what I'm going to do is now look at like this cross section right here by imagining my eye being right here. Okay, so when I look at that cross section, sorry, my pad moved all of a sudden and made my circle go to crap. So this is a radius R like this. What I'm seeing in this is going to be very small. So I assume the magnetic field's roughly a constant all inside of here. So there's my magnetic field. And like I said, it's roughly a constant all over here. And it's going that way. And of course, the surface area is perpendicular to that, or it's actually parallel to the B, because the B is going to point into the page, and the surface area can point either into the page or out of the page. In this case, I'm saying into the page. So I'm going to get just basically, since it's uniform, the B, I'll say magnitude of B, times the integral of dA, which is just pi r squared B. So I now have the magnetic flux, which was part 2. I don't know why I chose to write that in green. Let me go over it again, so in case it doesn't come out that well in the notes. So BdA is equal to pi r squared B. Now step 3 is to use L is equal to N times phi B over the current that caused it. So I'm going to say L is equal to N over I times pi r squared, that's that, times B. So now I got to put in my B, which is mu 0 n I, get rid of that theta hat, I'm just talking about magnitude right now, over 2 pi, and this should be big R here, over 2 pi r. So now I have that. Got another student just came in. All right, so that's my self-inductance, or what we call inductance, which I told you has units of Henrys. I can now see that the pi here is going to cancel out with the pi here, and that I ultimately get mu 0. Oh, by the way, the I is going to cancel out with the I up here. I get mu 0 times n squared. So mu 0 n squared times r squared over 2 times big R, and that should be the inductance. There is a problem in your textbook that asks you to solve this very problem. Let me tell you what number it is right now. I forgot to remember what it was. It's problem number 74. You can look at that and verify that this is exactly the same thing as they got, except they didn't use little r for this radius of this. They used little d for the diameter. So you could also do that. And of course, when you do that, that means this becomes d over 2 squared, which would make a 4 down here. So anyways, that is the self-inductance of a toroid. Any questions on that? So again, we are not in the chapter on Ampere's law. I did all this extra stuff showing you Ampere's law, and we're not on the chapter on magnetic flux. I did all this again to review magnetic flux. We are on the chapter in inductance, and the whole purpose of me showing you all this, just like it was in the last class, was to remind you that these are capstone problems that you should be able to accomplish, that everybody should be able to accomplish by the end of the semester. Okay, so make sure you work on these. There's really only 3 of them. I can soup them up, of course. I've told you about ways I could soup them up with regards to making the for instance, the current density, or excuse me, the charge density rho could be proportional to the radius, or the linear charge density lambda could be proportional to x or x squared or something crazy like that. But other than that, there's not much I can do to change it. It just has to be cylindrical, spherical, or planar in the case of the Gauss's law problems going into capacitance. And in this case, it has to be solenoidal, toroidal, or coaxial. And coaxial was another case, by the way, in the Gauss's law. So now that we have this, let's do another example. This will be example 2. So no questions on this one? Everybody understands that? So what I want to find is, what is L? Whoa, if, actually started writing the R, if big R is equal to 70.0 centimeters. So this is a big solenoid. This is literally 70 centimeters. This dimension is 70 centimeters. So that's a pretty big distance there. N is going to be 1,000 turns. That's really not that many turns, believe it or not. I've wrapped my solenoids myself. I've wrapped them in 1,200, 2,000, 2,500. Of course, if you use a lathe, it's a little easier. And I want to say R is equal to 1.00 centimeters. So let's see if we can calculate what that would be. Well, according to this, L is equal to mu 0 N squared R squared over 2 times big R. So that's 4 pi times 10 to the negative 7th Tesla meters per amp times 1,000 squared times R squared, which would be 1.00 times 10 to the negative 3rd, 10 to the negative 2, excuse me, negative 2 meters. And that's squared as well. All of that divided by 2 times big R, which is 70.0 times 10 to the negative 2 meters. Again, notice everything had to be in meters. So this one gives me meters squared over meters. And then that cancels out one of those, leaving a meters, but then I have a Tesla meter squared per amp. And of course, a Tesla meter squared is a Weber, and this is a Weber per amp, which is a Henry. So we know that Tesla meter squared is equal to a Weber, and a Weber per amp is equal to a Henry. Okay, so that's the stuff I'm using to make my units work out right. When I put that in my calculator, I did this earlier, make sure you guys can do this calculation as well. I got 897.597 Henries, which of course, this is only 3 sig figs. We should really call 898 Henries. Anybody able to verify that? Or better yet, or anybody able to say I made a boo-boo? Any questions on that? So this is actually the kind of thing that Michael Faraday had made when he was doing experiments. In fact, he had one, I think it weighed a couple 100 pounds. It was actually had it filled with a big block of iron in the middle of it. So he had wire wrapped around it all around here, but he had a big iron ring inside of it that was on the order of like 4 or 5 inches in diameter. And then this was on the order of maybe 20, 30 centimeters in radius. And of course, it was super heavy, but he used that to conduct a lot of experiments so he could make sense out of things like inductance and that sort of thing. And that actually is in a museum at Cambridge, if I'm not mistaken. But anyways, that is rather important. And really, they were studying it only in ways where the inductance had to be really large or they wouldn't be able to detect it. So no questions on that? All right, so I'm going to go out of the example mode right now and go back to a derivation type mode. We've talked about inductance, and I wanted to work out what the energy stored in an inductor is. Just like before, when we were working with capacitors, we tried to find out what was the energy stored in a capacitor, and we got a specific formula for a capacitor that turned out to be exactly right. Even though it was done for a capacitor, it happened to be exactly right for all energy stored, specifically in electric fields. So we're going to sort of do the same thing now. So we'll start off with P equals IV. Only, of course, we've been using the electromotive force, so we like to write P equals IE instead of IV, and it's pi. So I kind of like that anyways. But in this case, we have I is equal, or excuse me, we have E is equal to L di dt. So if you look at this, you can say, well, P is equal to dW dt. So that gives me the idea that in some sense, there might be a differential change in W, which really doesn't work that way, but we're going to do it anyway. So if we want to feel nice about the mathematics of it, we should put a little slash on there. because in principle, work is not a exact function. It depends on the path. But either way, we can say that's equal to P dt, and then combine that with that. And what we'll get is P dt is IL di. So what I'm going to do is say it's equal to L I di, and then U, which is the work done, is equal to the integral of, again, d bar W. And I have to put a bar on there, like I said, because it does depend on the path, but we're luckily able to sort of ignore that right now. So I'm going to now take that and substitute it in there, and I'll get L times the integral of I di. And what I have is the energy stored will be 1/2 Li squared. So U for an inductor is equal to 1/2 Li squared, just like U, the energy stored for a capacitor, was 1/2 CV squared. So you should think that capacitance, inductance are similar things, but maybe the inductance depends more on the current and the capacitance depends more on the voltage. That's sort of a thing you should think about, and you would be right. And we're going to see how that works out when we start to deal with circuits. But it's also not unlike 1/2 mv squared versus 1/2 kx squared, which we studied in harmonic motion. So you can see, just like when we had harmonic motion on a spring, we had a kinetic energy and a potential energy, where energy would slosh back and forth between all of this and all of that, and then some mixture of each. So when we put these in a circuit, we're actually going to find that that actually is the case. We'll have an energy sloshing back and forth between the energy of the inductor and the energy in the capacitor, which ultimately turns out to be the energy in the magnetic field or the energy in the electric field in that case. So that brings me to the next part, which is, let's consider the energy just in an inductor. So we're going to take this idea and think about it in an inductor, but I'm going to use a specific case, just like I did with the capacitor. I chose the parallel plate capacitor and got a relationship for this in terms of the geometry of the capacitor in some sense. And then ultimately I was able to relate it to the electric field. I'm going to do the same thing now, only I'm going to use the solenoid, where here I use the capacitance. So I'm going to say 1/2, and then of course we worked it out before that the inductance of a solenoid was mu0 n squared A over L. It was actually mu0 times little n, but that's big N over L. So mu0 n squared A over L is the actual L that I'm using there. And then we also knew that the magnetic field for an actual inductor was mu0. Actually, it was what, mu0 L, mu0 I times big N. So if you solve that for I in terms of the magnetic field, you end up getting B times L over mu0 times N. And of course, this I is actually squared. So this is the formula of basically for the magnetic field and for a solenoid, only we've solved it for a current instead of for the solenoid. Because remember, for the magnetic field, it was mu0 N times mu0 N over L for the solenoid. So B equals mu0 N times I for the solenoid, but this N is N over L, so that's why we got the N here and the L there. So does that make sense, everybody? If I solve this for I get B0 over or B over mu0 N, but N is N over L, so that's why I got that. Well, once you work out all this, of course, all these things are going to be squared. What you end up getting is 1/2 of mu0. There's an N squared there. There's an A here. There's a B squared here, an L squared here, and then there's a L down here and a mu zero down here. Oh, it's mu zero squared, excuse me, and an N squared down here. So what you see is the mu zeros are going to cancel out, leaving a single mu zero here. The L is going to cancel out, leaving one up here. The A is going to leave one up here. And I ultimately get 1/2 B squared over mu zero times A times L, which, by the way, happens to be the volume of the solenoid. So we find the current density, which is U over the volume. I'm doing this so the V doesn't look like a voltage. That energy per unit volume turns out to be 1/2 B squared over mu zero, which was like epsilon 0 E squared that we found before. Okay. So again, we see another way where magnetic field and the electric field look like sort of two sides of the same coin, and that is ultimately what Maxwell's equations brings us, is that the B and the L, or excuse me, the B and the E are just two sides of the same coin. And in fact, you can switch from one frame to another such that a magnetic field disappears and becomes an electric field that gives you the exact same physics as the case when you treat it as a magnetic field. So any questions on that? Okay, so that right there, forget this, I hate this. This thing goes to pull, it almost always rips across there, and then it aggravates the OCD in me for the whole semester. Let go, darn you. I'm going to shoot that down. Okay, so what we've done now, we did example 1, where we derived the inductance for a toroid. We did example 2, where we used that result for the inductance of a toroid to calculate the inductance for an actual toroid. And now I've derived the energy stored in an inductor, compared it to the energy stored in a capacitor, and now I've derived the energy density of a magnetic field and compared it to the energy density of an electric field. So we've done quite a lot, but that brings me now to another issue. So now that we've sort of understood the basics of inductors and capacitors, now we can start talking about, well, what happens when we put them in a circuit. So I'm going to start off with an LR circuit. So let's imagine that we have a battery, a voltage V0, parallel, if you will, to just a plain wire, and that there's a switch that can cause this to go from either the plain wire or to the battery, or from the battery to the plain wire, or just in between them. And then I'm going to run around here and put a resistor R, and then an inductor. This is a symbol for an inductor, as we mentioned before, of L. Okay. Now, if I were to throw this switch over here to V0, then this voltage source, this battery, would start to create a current, but initially there would be zero current coming out of it, because it's going to try to create a current, but Lenz's law says that if the flux is increasing through an inductor, then Lenz's law says that a back EMF will be created such that it fights that change in flux. So it's actually going to fight it for a split second, and we'll have a zero current initially. But as time goes by, the change in flux will get smaller and smaller, so the fighting will get smaller and smaller until eventually it will just make a static situation in which a fixed amount of current is flowing around through the battery, through the resistor, through the inductor, and then back through the battery, so on and so forth. And we're going to use a differential equation, or set up a differential equation to show that. So first off, I'm going to take Kirchhoff's loop rule, the KLR, right? And I'm going to see this is a voltage increase of V0. And then that's going to lead to a voltage decrease of, because this is the current I equals I of T going through there. Okay. So I'm going to say this is minus R times I, and I'm putting the I second because the differential equation is going to be in terms of I. So it makes sense to do that. And then, of course, there's going to be a further voltage drop across here that's going to be negative L di dt. Now we're back to where we started in the loop, so we can say that's equal to 0. With a little bit of work, you can change that to V0 equals L di dt plus Ri. And with a little bit more work, you can change that to di over V0 minus I, or excuse me, minus Ri, like that, is equal to dt over L. Okay. Now I can integrate both sides. I'm going to integrate from I equals 0 to I of T, really, but we'll just call it I because it's a pain in the butt to write that. And this is going to integrate from 0 to T. So to do this integral, we're going to make a substitution. We're going to say, let U equal V0 minus Ri. Then du is going to equal negative R di, so that di is going to be negative 1 over R times du. So I can replace this di with negative 1 over R. When I do that, I am going to get negative 1 over R integral du over u is equal to, we already know what this integral is going to be. It's just going to be 1 over L times T. So now we can integrate this, and I'm going to get the natural log of u, and that has to be evaluated at I equals 0 and first at I equals I of T. So I'm going to now say that this is the natural log of V0 minus I, or excuse me, minus R. I keep wanting to write the I first, and I can in a second, but I probably should stick it here for right now. And this case was the I equals 0 case, so that's just V0. Now what I've done is I went ahead and pulled this over here and made it equal to negative T over L over R, because tau, the time constant for an LR circuit, is going to be L over R. So notice, unlike the RC circuit, tau for the RC circuit was R times C. So the higher the R, the larger the time constant. In this case, it's L over R. So the higher the R, the smaller the time constant. And you don't necessarily see that yet, but you will in a second, because now I'm going to raise both sides of this equation. I'm going to raise e to that power. So in doing that, I get V0 minus IR. So this is the place where it's okay to write the I first, is equal to V0 times e to the negative T over tau. Again, just using tau for that. Now I can get that V0 times 1 minus e to the negative T over tau is equal to I times R, or finally I of T, which is just that I there, is equal to V0 over R times 1 minus e to the negative T over tau. So basically, this is the time required. This tau is the time required for it to reach about 63% of the maximum current. If you allow T to approach infinity, this becomes 1 over e to the infinity, which is essentially 0. So as time goes to infinity, you expect the current to reach V0R, which is exactly what it would reach if this L was just a regular piece of wire. So that makes a little sense. And in fact, you can make a plot of I versus T like this. And what you're going to see is it starts at 0 and it sort of asymptotically approaches V0 over R. But if you come over here to tau, it's going to reach 0.63 V0 over R. So that's how a LR circuit acts when you first connect it to a battery. Now let's imagine that it's been connected to the battery and it actually has a current I going through it, and let's disconnect this. So we're going to throw the switch now from here back over to there and see what happens. Current goes from I to I equals 0. This one was current. Went from I equals 0 to I of t. Okay. So that was that. This is this case. Now, in this case, what we have really is just a resistance R and a current I and a inductor L, and the current's going this way. So we can use Kirchhoff's loop rule again. And basically what we're going to say is there was initially a voltage V0 that was driving all this, right? And the current's still going to be dissipated by an amount IR, or excuse me, the voltage is still going to be dissipated by an amount IR, and then by an amount L di dt. So Kirchhoff's loop rule again tells us negative Ri minus L di dt is equal to 0. So this one's a little bit easier to solve. What I'm going to do first is divide both sides by L, and I'll get negative R over L times I is equal to, actually, since I went ahead and said equals to, I'll make this a plus because I'll bring this to that side and that'll become positive. I think, right? Yeah, I can become positive. This will become negative. Actually, no, this will, I'll keep this as negative. My fault. Sorry about that. So this is negative R over L times I. And then over here, I'm going to have just di over dt, which makes a nice differential equation, specifically saying the integral of di over I. So I can pull this over there, in other words, and this would be equals negative R over L dt from 0 to t. And this is going to be from I to I equals 0. Or actually, we shouldn't say from I to I equals 0. We should just say from I to I of t. Okay. That way it frees us up to get a general expression for it. So this side's just going to become the natural log of I of t over I 0. Okay. And this side is going to become negative R over L times t. Again, I raise e to the left-hand side power and e to the negative right-hand side power, excuse me, and set them equal to each other. And then I get I of t is equal to I0 times e to the negative t again over tau, because R over L times t is the same thing as t divided by L over R. So we got another valuable expression that helps us. And in fact, this one is just a classic exponential decay. You can make a plot of it if you'd like. And this is t, and this is I. And basically, we start off from I0 and fall down like this, approaching 0 over time. But in fact, in a time tau, it'll reach 0.37 I0. Notice that's the reciprocal, or that's the additive inverse, if you will. In other words, the sort of parenthesis, the sort of percentage-wise inverse of the 0.63 that we got for. In other words, when this adds to this, it gives you 1. So anyways, that's basically the behavior of an LR circuit, both when you first plug it in and then when you disconnect it. Anybody have any questions on that? All right, well, let's work an example using these results so you'll have some sense of, how they're used. Now, your job is not to be able to derive this. I mean, you should be able to derive it like as part of your note taking, as part of your learning in physics. But what I'm requiring of you in classroom and during tests is your ability to use these results like this equation or this equation to apply to solve certain problems. Okay, so just keep that in mind. Sometimes there's some ambiguity as to what I expect of you versus what you think is expected of you. I've made explicit that those derivations of the capacitance and inductance formulas are something you should be able to do. And now I'm telling you, this is something you should be able to do with the little aid of looking at a book every now and again, but it's not something you should be able to do during a test. Okay. All right. With that in mind, let's consider at t equals 0, a 12.0 volt battery is connected to a 400.0 millihenry inductor in series with a 50 ohm capacitor. I said capacitor, a 50 ohm resistor, sorry. The questions I want answered are A, what is the time constant? B, what is the max current? Notice I'm using a different terminology for it now. I actually just gave you the formula for the max current earlier. Now I'm calling it Imax. That's just the way that we sort of make sure you understand what you're talking about. You would maybe call it a trick question, but it's not meant to be a trick question. It's meant to make sure you understand the entirety of the situation, or of the concept. So in part C, I'm going to ask you, what's the current I of t equals 0? In part D, I'm going to ask you how long before I equals 1/2 I max. Again, I'm using that new terminology. Part E, I'm asking how long before I equals 0.999, in other words, 99.9% of I max. Okay. F, I'm going to ask you how much power the battery is supplying when I equals 1/2 I max. And G, how much, it's the same time, by the way, how much power is going into the B field. In other words, the magnetic field created inside by the inductor. Okay. So those are our questions. Obviously, I don't have enough room to work it at the bottom of this page, so I'm going to tear it off again and try to keep it closer like this so that we can see the problems as we're solving them. Okay. So first off, part A. So part A, we're asked, what is the circuit's time constant? Well, the circuit's time constant, tau, is equal to L over R. So that's 400.0 times 10 to the negative third henries over 50.0 ohms. Well, we know that 400 divided by 50 is 8. So I'm going to call this 8.00 times 10 to the negative third seconds, which is, of course, 8.00 milliseconds. So that's the time constant. In other words, it will take 8 milliseconds for the circuit to go from 0 to 0.63 times the max current. Now, part of an exercise, you should be able to show, and you can do this as like an extra credit thing if you want, but you should be able to show that henries divided by ohms actually gives you seconds. I've sort of given you a hint to that in the first page of notes, but anyways, you can go from there. So there's part A. Part B, I'm asking you, what is I max? Well, if you look at the equation says I is equal to V0 over R times 1 minus e to the negative t over tau. So you can see as t approaches infinity, this goes to 0. So it should be V0 over R. So I max is equal to V0 over R, which is 12.0 volts over 50.0 ohms. Now, if I multiply this bottom by 2, I'd have to multiply the top by 2. That's not a big deal. That would be 24. But I know 24 divided by 100 is just 0.24. So the math works out really nice by considering that. So 0.240 amps, which equals 240 milliamps, is the right answer to that. So I don't have to actually use a calculator, in other words. Okay. Part C, I'm asking you, what is the current at t equals 0? Can anybody tell me what that would be?
Is it 200? I think it's 290 milliamps.
Oh, that's a 40, by the way.
Oh, 240.
Yeah, but no, that's the current after it's been allowed to go for about an infinity of time. Okay. Do you recall? This is more like the first problem. Do you recall what the current has to start at, or what's fighting it from starting up? Thank you.
Okay. Voltage back is fighting.
Yeah, it's got a back EMF caused by Lenz's law and Faraday's law. When you're trying to increase the current through the inductor or Lenz's law fights that, which is really just a conservation of energy thing. So it actually creates a back EMF. So initially, even though you connected it, it can't get initial current bigger than 0. So the answer is 0 on that one. But thanks for trying. Like I said, I want you guys to answer so y'all can, stay engaged or whatever. All right, so we've got part C done. This might take just a little bit of reading to make more sense of this. I've sort of given it to you in the spoken word, and the spoken word's a little harder to deal with than the written word because you can reread the written word over and over and over again. So don't worry, it'll be making a little bit more sense the second, third, or fourth time you read it. So now part D, I said, how long before I is equal to 1/2 I max? So what that means is I'm wanting 1/2 V0 over R is equal to this. So I'm going to say that's V0 over R times 1 minus e to the negative t over tau. When you see that, the V0 over R cancels out, and I get basically 1/2 equals 1 minus e to the negative t over tau, which gives me e to the negative t over tau is equal to 1/2, I can take the natural log of both sides and I get the ln of negative t over tau is equal to the ln of 1/2. The rules of ln dictate that if I switch this to the, excuse me, this negative here, what's going on here? T over tau, e to the negative t over tau. If I wish to change this negative, I can take that to be 2, the ln of 2. So ultimately, I'm going to get t equals 2, or excuse me, t equals tau times the ln of 2. Okay, the ln of 2 is about 0.693. So you can multiply 8 milliseconds times 0.693. And ultimately, when you do that, you're going to get basically 0.00545 seconds, which equals 5.45 milliseconds. Now, that's a small amount of time for it to reach half the value, but that's also why I went ahead and asked you to do part E, which is how long would it take to get 99.9%? So 0.999 V0 over R. Remember, that's I max is V0 over R. That's equal to V0 over R times 1 minus e to the negative t over RC, or excuse me, over tau. Oh, stupid me. I hemmed and hawed a little bit. When I take the natural log of the left-hand side here, that just became negative t over tau. Sorry about that. So that just became negative t over tau, not the ln of it. That's what I was screwing up with. But you can take this negative and multiply it by both sides by -1, and you get negative ln of 1/2. But a negative multiplied by a logarithm is the same thing as raising the argument of the logarithm to the power of the multiplier. In this case, the multiplier was -1. So you'd raise 1/2 to the negative 1/2, to the negative 1 power, and 1/2 to the negative 1 power is just 2. So that's where that came from. Sorry about that. So now this V0 over R again cancels out, and I end up getting 1 minus 0.999 is equal to e to the negative t over tau. That 0.001 is equal to e to the negative t over tau. Now I'll take the natural log of both sides, and I get the ln of 0.001 is equal to negative t over tau. But again, if I multiply both sides by -1, I get -1 times the ln of 0.001 is equal to t over tau. If this becomes a exponent on 0.001, this is 1/1000. So when I raise it to the -1 power, it'll be 1,000. So ultimately what I get is t is equal to 1,000 times, excuse me, t is equal to tau times the ln of 1,000. Okay. In that case, t turns out to be 55.3 milliseconds. Okay, so you can see that's still 0.05 seconds. So yeah, it's going to reach that really quickly. And in order for you to see something like that occur, you'd obviously have to use an oscilloscope with a capture function where it could actually capture it. So I'm going to go ahead back and circle these answers. That was D. That was C. All right, any questions on that one? Okay, now let's bring it back down so I can see the question again. So we're now up to part F. And in part F, I asked you how much power the battery is supplying when it's actually got that current that we had for the 1/2 mark, the 0.240 amps. So for part F, P is equal to I times V. Well, the current is 0.12. Sorry about that, because remember the max current is 240 milliamps. The max current is 240 milliamps. I want to know what is the power delivered when it's half of that, which is 0.120 instead of 0.24. So 0.120 amps times the voltage of the battery, which is 12.0 volts. And I think you can see that's 1.44 watts. So that's the power delivered by the battery when I equals 1/2 I max. Okay. Now G is a little different. G is where I'm asking you at what rate is energy being stored in the magnetic field. Well, that's du dt is what power is, like it always is. It's either dw over dt or du over dt. And we know that U was equal to I times L times di dt. So I'm going to say I times L di dt. And with this one, I can just go back and use the differential equation that I had to substitute all this. And what I'd ultimately get for this case is just I times V0 minus Ri. Well, that I, again, is the 0.12. So I'm going to say 0.12 amps times 12.0 volts minus 50.0 ohms times 0.12 amps. Again, should be 3 sig figs there, even though I dropped it down to 2 for a second. And that actually gives me 0.720 watts. Okay. So there's the answer for F, and this is the answer for G. So anybody have any idea what's going on with the rest of the energy? The battery supplying 1.44 watts. The magnetic field is only accepting 0.72 watts. There's another 0.72 watts that's not being accounted for. Anybody have an idea where that wattage might be going?
It's going into the resistor and dissipated.
Exactly. P equals IV, which becomes I squared R for the actual resistor. So yeah, it's the rest of it, the 0.72 is going into the resistor. Any questions on that?
Based on the numbers, looking at it, I just have a question about, I don't know if this is happenstance or if you plan this, but it looks like the voltage drop across the resistor and the inductor are about the same.
Yeah, that's not always the case with circuits that involve L, R, and C. And that's what we're going to learn about next, is when we start to talk about not just an LR circuit, we might talk about a LC circuit. And then we're going to talk about an LRC circuit. The sum of them at any instant in time will be equal to the voltage of the source at that instant in time. So in other words, if we combine this circuit with an actual AC power source, at any instant in time, the power source is going to be swiggling like that, right? Or wiggling up and down between a maximum voltage and a minimum voltage, or maximum backwards voltage. At any instant in time, the voltage across the capacitor plus the voltage across the resistor plus the voltage across the inductor will equal exactly the total voltage coming out of the power supply. This just happened to be the case because we were only doing L and R. If you only did L and R, or if you only did R and C, you would find what you just noticed, which was that they're about equal to each other. Good question, though. Anybody else have anything? All right, so what we've done now is basically handle LR circuit. And by the way, let me stop for a second and give you some explanation of what's going on here. physically speaking, you can use a inductor and a capacitor in various ways. In fact, we can use a capacitor, which we didn't have in this particular circuit. We can use a capacitor to do neat things. Specifically, a capacitor, if you put it, say, here's a circuit, and you just run a line from one circuit through the capacitor to the next circuit, what you're going to find out is a capacitor for a DC circuit is essentially an open circuit, right? It's literally a break in the wire. Like if you put a battery and connect it to a capacitor, basically what's going to happen is current's going to flow just to try to make the charges on the left-hand side of that capacitor accumulate positively. That's going to force the charges, the positive charges on the right-hand side, to run away and go back in the battery until the voltage across that capacitor is the same as the voltage of the battery. But once that happens, no more current flows. And in some sense, current never flowed. It was more like you just induced charges to run away from the right-hand plate, right? So you should always think of a capacitor as an open circuit for DC. So if you have a circuit with a wire going through a capacitor and then to another circuit, that's job of that capacitor is to cut out the basically the DC voltage. So why would you want to cut out the DC voltage? Well, if you have a stereo, you have a woofer and a tweeter, right? In your speakers. So in a loudspeaker, you have a woofer, which handles the low frequency sound, and you have a tweeter, which handles the high frequency sound, the treble. Okay, so the woofer does the bass and the tweeter does the treble. So with that in mind, if you actually put a capacitor in series with the tweeter, then that's going to cut out all the bass from coming through there. Or excuse me, if you put a capacitor in series with the woofer, that's only going to allow the high frequency stuff. So that would ruin the woofer. Whereas if you put a capacitor in series with the tweeter, that would cut out all the low frequency stuff and just allow the high frequency stuff. Well, it turns out that a inductor behaves exactly the opposite. So if you put a circuit with an inductor in series and then another circuit right here, that more or less cuts out the AC stuff, and at least the high frequency AC stuff, and only allows the DC stuff, in other words, the low frequency. So you could use an inductor in front of the woofer, and that would actually allow only the bass sound to come through. So those are some different applications, if you will, of circuits. And in fact, when you have a capacitor like we had, where it basically went from a circuit to a capacitor to another circuit, that's what we call a basically a high pass filter. The reason why I call it high pass is because only high frequencies can go through a capacitor with little or no distortion. However, if you take that circuit, run a wire, and then run a wire to ground and put a capacitor right there, and then go right to ground, and then continue that wire straight onto the other circuit, then in that case, all the AC is going to run straight to ground, and all the low frequency stuff is going to go to the other circuit, and that's called a low pass filter. And it turns out, if you study electronics enough, like if you go into double E, you'll also call a high pass filter a differentiating circuit and a low pass filter a integrating circuit, because you literally can write differential equations using op amps and things like that to solve differential equations. And what it'll do is you put in whatever functions you want, and out pops the solution to your differential equation as a graph on the oscilloscope. So it's kind of neat little stuff about that. The next thing I wanted to do, we just did an LR circuit, so now I want to do a LC circuit. And this is a construction that's more or less imaginary, because with an LC circuit, that suggests there's no resistance whatsoever. And even a wire has resistance, so it's not really a real scenario, but it's an extreme case that we can imagine as a goal when you allow the resistance to be very small compared to the inductance and reactant, or the inductance and the capacitance. So let's look at that now. So what we're going to do is we're now going to imagine, and actually I need to do this. What we're going to do is now we're going to imagine an LR circuit. Make sure I'm on the page. Yeah. Okay. So we're going to have a capacitor right here, and it's positively charged. Okay. And it's going to be in series with an inductor. This inductor has an inductance L. This capacitance has a capacitance C. And what we're going to say is that the capacitance has an initial charge Q0. Okay. Now, if I apply Kirchhoff's loop rule, what I'm going to see is I'll go from here to here and I'll go up. Remember, C is equal to Q over V. So V is equal to Q times C. So from here to here, I'll go up an amount Q0 times C. In general, however, that would be just the charge on it as a function of time times C. So I'll say Q times C is the voltage up, and then minus L di dt. That's the voltage drop across here. And now I've completed the circle. So Kirchhoff's loop rule is giving me this. Again, this is Kirchhoff's loop rule.
Professor Dr. Younger, isn't
Yes.
The equation for V equals QC supposed to be V equals Q over C?
Oh,
Like C equals Q over V, and then you solve for V. I think it's supposed to be
oh,
V
thank you.
equals Q over C.
Yeah, I don't know what I was thinking there. God, that's horrible. Thanks. Nice catch, bud. Appreciate that.
Yeah, no problem.
I'm solving differential equations and I make a mistake on basic arithmetic and algebra. So yeah, V is equal to Q over C. Whoa. And that would have showed its ugly head in a second. So I really appreciate you doing that. So that's 1 over C times Q is what I'll call that. I don't know what I was thinking, but thanks again. So now that we had that, we can also realize that I is actually related to dq over dt, but in fact, it's a little bit different because I is actually negative dq dt because the Q was the charge on this, right? And if this charge decreases, that means the current is going to be in a positive direction. So we have to put a negative there. So that ultimately gets us back to 1 over C times Q plus L d2Q over dt squared is equal to 0. So I can now write the differential equation as d2Q over dt squared plus Q over LC is equal to 0. So this equation, well, let me write it a little bit better and then it'll make more sense to you. d2Q over dt squared plus, you might write 0 dq dt, but I'm not going to choose to write that. And then you say plus 1 over LC times Q is equal to 0. And then I think you can see it's a harmonic oscillator differential equation. And it has a very specific form. We can say Q of T is equal to some Q0 times cosine omega T plus phi. We know that happens to be one of the solutions. If you're taking differential equations, we'll usually use e to the rho x or e to some constant times x. And then we take the derivatives, plug them all in here, and then realize it has to be true for at all times. So you pull out the e to the rho x or e to the rho t, and then you're left with what they call a characteristic equation. And that characteristic equation allows you to find a relationship between omega and L and C. So that's more or less what we're going to do here, except we're not using the E's, we're just using the cosines from the beginning. Okay, so this is like what you're doing in differential equations or what you have done in differential equations or what you will do, only we know that ultimately we're going to want everything in terms of a sine or a cosine. So we start off with the trig functions. I particularly do not like starting off with the trig functions. I'd rather do it the way they do in the math class. But anyways, so now that I see that, I can say, well, dq dt is equal to, take the derivative of this, I'm going to get Q0 times cosine. Well, actually, I'm going to take the derivative of cosine with respect to time. And of course, the derivative of cosine is equal to negative sine. So I'll put a negative here, and then I'll do sine omega t plus phi. But now I got to take the derivative of the argument, which is omega t plus phi. And of course, phi is a constant. We call it the phase constant. So I end up getting a negative omega q0. Now I take the second derivative, d2q over dt squared. And in that case, I'm trying to keep an eye on the time. In that case, now I'm going to take the derivative of sine, which is cosine. So I'll keep my negative. And now I have omega squared q0 cosine omega t plus phi. So that's basically what we have for the second order derivative. I don't actually have a first order derivative in here, so I plug this back in. You can see there's a common factor of q0 cosine omega t. So what I'm going to do is I'm going to say negative omega squared plus 1 over LC times q0 cosine omega t plus phi is equal to 0. That's what I get when I plug this in here and this in here. So you can see, in fact, that omega, because this has to be true at all time t, it can only be true at all time t when this factor right here is equal to 0. So that means omega has got to equal 1 over the square root of LC. Okay, and by the way, omega is equal to 2 pi f, just in case you forgot from last semester. Okay, we never take a positive, we never take a negative because it's an angular frequency, and we always treat them as non-vector quantities as positive. Okay, so that's ultimately what happens. If we look at that, we can see that the I, which equals negative dq dt, is negative times a negative. That gives me plus omega q0 sine omega t plus phi. And I'm showing you this for a very specific reason. Now that we have that I, we can then say u, which equals 1/2 Li squared, is going to become basically some stuff times sine squared. Whereas u, that was for the inductor, u for the capacitor is going to be 1/2 c times some v squared. Well, v is just going to be the I times the r. So you're going to end up getting the sine squared there. If you actually make a plot of these energies, what you'll see, and this is why I'm doing this to begin with, and your book has this as equation, as figure 3012. Basically, what you have is one graph that looks like this. Okay, and that's actually the energy in the electric field. In other words, we start off with that, and then we substitute in the C and the L and all that good stuff. And what we're going to get is that the capacitance one, which is 1/2 CV squared, that capacitance one, when you go and convert that to the electric field, you're going to get something that's a cosine. And then when you do the electric field one, you're going to get something that actually looks like this. And I find this kind of wonderful because if you think of everything as if it's a cosine, and you think of the angle, the phase angle 0, then what you see is the energy in the electric field, which is the capacitor, in other words. The energy in the capacitor starts off high, and then 90 degrees later, the energy in the inductor is high. That turns out to be what we call Eli. And actually, there's another part to it. Eli, the ice man. This is an old adage from electricity and magnetism and electronics. It basically says that the voltage is in front of, notice it reached a peak first here. It's in front of the current, which peaked here by 90 degrees basically. And it's always 90 degrees, but Eli the Iceman is something that we use, and we'll use that next for LRC circuit so that we can actually figure out how to deal with a circuit that has a resistance, a capacitance, and an inductance all in it. But this is the first time you actually get to see that there's a slight delay. In fact, because the energy in an inductor is the current, and notice the current is a maximum for the inductor only when the energy in the magnetic field is a maximum. So right here, the current is a maximum. Right here, the voltage is a maximum. And this voltage maximum was at T equals 0, whereas this current maximum was at T equal, basically 2 pi. Well, it's actually a multiple of 90, in some sense, 90 degrees, or pi over 2. So anyways, that's basically enough for today. We're up to the 6:03 minute mark. I ran over last time, so we'll call that a day. And next time we will go ahead and finish off chapter 30. I'll wait for the last person to leave in case any of you have any questions. Other than that, you're free to go.
Have a good night, Professor.
You too. Thank you, everybody. James, did you have any questions?